Welcome to Lesson 6. So we're going to talk about one sample Z methods for a proportion. So we're going to be looking at when we're collecting a categorical variable, breaking it up into two categories, and looking at the proportion for one particular group. So maybe we want to know the proportion of all OSU students that have ever taken out student loans. That kind of idea. So objectives here. This is just kind of introducing both here. One proportion, we're going to define p hat again and its sampling distribution. So what the sample proportion looks like after you take sample after sample. We're going to look at performing a large sample confidence interval. So we're going to calculate a confidence interval. Our next thought should be, hey, we're going to do a hypothesis test. And we're going to calculate a sample size. So that is the scenario where you say, hey, I want to have a confidence interval with a certain confidence level, and I don't want it to be any wider than a certain amount. And then we determine, well, how large of a sample would we need to be able to guarantee that. And then lesson 7 is going to get at two proportions. So we're going to define P1 hat and P2 hat, and that the sampling distribution of the difference of P1 hat minus P2 hat. We're going to calculate a confidence interval for that and a hypothesis test as well. So proportions. So this is a throwback to types of variables. Up until now, for the most part, we've been dealing with quantitative variables, so those are values that make sense to average. But this will be when we're looking at a categorical variable, specifically one that we can break into two categories. So, for example, the proportion of OSU students that spent more than $100 on textbooks during a particular term is 0.78, which I don't really know what that value is. But the idea is I'm saying, hey, the proportion of this entire group that has this characteristic of interest is value. Proportions, because of the way they're written, they have to be between 0 and 1. If you write them as a percentage, you must include the percent sign. That is incredibly important. But proportions, they're going to always be between 0 and 1. They can equal 0 and they can equal 1, although they admittedly aren't as interesting when they do. A proportion of 0 means it never ever happened, and a proportion of 1 means it always happened, guaranteed. So the general wording here, it is a little bit different wording than when you had a quantitative variable. The proportion of whatever your group of interest is, that, and then has a particular variable of interest, is, and then either like a number or a range of values. So the proportion of all U.S. adults that are registered to vote is blank. So throw back to our types of variables, quantitative variables. We typically summarize these using a mean or median. Up until this point, we've always looked at means. We will look a little bit at medians. We can describe the spread. Either we can use the standard deviation or we can use the IQR, so the interquartile range. So examples, height, weight, distance, volume. There are a lot of quantitative variables out there. So the big thing is these are variables that are numeric, and they're variables that make sense to take an average of. It would make sense to average them. A counterexample would be weirdly zip codes. They are numeric, but they make no sense to average because the zip codes represent categories. So hypothesis tests. So we have so far looked at z-test for a mean. So when we're testing a single mean and we know sigma. A t-test for a mean or a t-test for a difference in two means. And match pairs t-test. Categorical variables. So these we tend to summarize with proportions or percentages. So be careful, if you use percentages, you should include that percent sign. It's really, really important to include the sign, because if you write it as a percentage, but you don't include the percent sign, it's a much, much different answer. Basically, imagine your answer times 100. It could be drastically different. So example, gender and sex are used a lot in stats. There a lot of times they're used interchangeably, just a caution. Eye color, so maybe brown, blue, green, whatever colors you want to include there. Major, day of the week, grade level, etc. So these are typically, they're not numeric. If they are numeric, they're numbers that don't make any sense to average. So something like a zip code or a phone number or ID numbers, that kind of idea. But a lot of times, if what you're collecting, the variable you're actually recording on individuals, if it's a word rather than a number, it's going to be a categorical variable most of the time. So our hypothesis test for this, we are actually going to use Z methods. So we'll have a Z test for proportions. So we'll have a Z test for a single proportion, and we'll have a Z test for a difference in two proportions. And that's what we are looking at this week. And then chi-square tests. So that's going to be in week 7. And that chi-squared, this is when you have a categorical variable and you don't break it up into only 2 groups. You might have it broken up into more than 2 groups. This week we're going to have a categorical variable, and there can be more than 2 categories, but ultimately we break it up into 2 groups. You might say, okay, well, I want to look at proportion of students born on Monday that are born on Mondays. Well, you can break it into Mondays and every day besides Monday. You can break it up into 2 categories. That kind of idea. So the example we're going to use here, marijuana legalization's become a big thing across the country. It's mostly accessible medically. It's becoming more readily okayed recreationally, although it is not at the federal level. So at individual state levels, like in Oregon, it's legal recreationally. However, federally, it's not. So we decided to ask the class, what do you think? Do you think that marijuana should be legal for recreational use at the federal level? So at the countrywide level rather than the individual state. So sample proportion. In order to actually get at talking about this, we want to talk about the sample proportion here. So when we looked at quantitative variables, we looked at means, maybe medians, but so we looked at the sampled statistic x bar. When we have a categorical variable, we're going to look at p hat. So we're going to use a sample proportion p hat. So anytime you see this, it's like a little caret hat thing. It means that, hey, this was estimated using sample data. So anytime you see a hat, you should think, oh, this is something that's describing a sample. So if we don't know the true population proportion, and usually we don't, we're going to start by taking a sample and using the proportion we observe in that sample to estimate the proportion in the entire population. It's our best guess. It's our best place to start. So you could say that p hat is our point estimate for p, for the population. If I want to know the population proportion, the best place for me to start is going to be with a sample proportion. It's my best guess. So p hat, it's going to be defined as number of successes. And I like to put quotes here, not that you have to, in sample over the entire, so n is our total sample size. So number of successes is completely defined by, it's more of like number with the characteristic of interest. We might say, hey, what proportion of individuals have cancer, right? It's not what people traditionally think of as successful. It's it's more of like, hey, it's successful in the sense that the condition we're interested in is present, so we're going to count it. So no, success just means, hey, number of times that thing of interest pops up out of the total number in the sample. So how do we know if our p hat is a good estimator? So there are going to be factors like we're going to want to make sure we have a big enough sample size for starters. So the central limit theorem, that's where that comes in. If we have a big enough sample, that central limit theorem is going to kick in, and we're going to know how the sampling distribution of p hat is shaped. So what I'm saying is if I took all unique samples of 50 from a population and I calculate the sample proportion from all of them, I would know where that distribution of all the p hats that I could get would be centered, and I'd roughly know how it should be spread out, thanks to the central limit theorem. Well, given that a sample of 50 is big enough. So p hat, it's an unbiased estimate of p, which is good. It means that, hey, on average, p hat hits the mark. It is a good estimator for p. On average, it's hitting where on the target we want it to hit. So here we know, thanks to the central limit theorem, it's going to be the sampling distribution of p hat. It's going to be roughly normal. It's going to be centered at p, which is exactly what we usually want to be estimating. And it's going to have the standard deviation is going to be a little funkier. So it's the square root of p times 1 minus p over our sample size. And as our sample size, n, gets bigger and bigger, the spread gets smaller and smaller. And one way to think about it is if I were taking samples of 5 and calculating the proportion of students with brown eyes out of 5 students, that's going to fluctuate more from sample of 5 to sample of 5 than if I were to take a sample of 100, right? It's just not going to fluctuate as much when you have a larger sample size. So if n is large enough, and we are going to have to talk about what we mean by it, it's a little bit different than it was before. The sample statistic p hat, so the sampling distribution of p hat, we know it's going to be normally distributed. We know it's going to have a mean or a center of p, which usually is exactly what we want to estimate or test, and a standard deviation here. So now we have to get at what is large enough. So it is going to depend on whether or not we're doing a hypothesis test or a confidence interval. But let's just show you first what's going on with proportions in the central limit theorem. So we have, this is our population, and here you can see it's a fairly large population. It looks like 0.6, so 60% of the population has whatever condition, 40% don't. So if I were to take a random sample from this population, let's say I take samples of size 3. Well, I can have a scenario where 0 out of the 3 have the condition, 1 out of 3, 2 out of 3, or 3 out of 3 do. Right? So those are the only scenarios we can have. And this is how they're distributed. If I took all unique samples of size 3 that I possibly could from this population and calculated the p hat from all of them and recorded just those p hats, this would be the distribution I get. And so as you can see, I mean, there's sort of a curve shape. I mean, there's definitely some gaps in here. But let's increase the sample size because 3 is pretty small. So when I increased it to 30, look, that's doing a whole lot better. It really, really is. If I increase it even more to 100, this looks really good, right? Really nice and normal. This has us really happy. This is like, okay, like it, I wouldn't say it's fantastic, but it's not horrible. This first one is just really, really hard. Samples of 3 are really, really small. In general, you need to have a really, really good reason for taking samples that small. it's usually, nobody's going to be very happy with you if you take samples of 3, if you want to do a study. Okay, so back to this marijuana example. I went ahead, used the student survey at the beginning of the course, asked students, hey, what are your opinions? Do you think that marijuana should be legal recreationally at the federal level? So I had to I combined all 3 of my classes that I'm teaching this term. So these are my students this term. And let me see, where's the number? So in favor, we had 216 students in favor of marijuana being available recreationally at the federal level. We had 57 oppose. That put us at 273 total. So I had 273 students, 216 of them supported legalizing it federally. So my best guess is going to be P hat. So it's going to be my number of successes. So here, because we're interested in agree or support, it'll be 216 over 273. And absolutely, if you had reworded the question so it was proportion of all OSU students that oppose, then you would have put the 57 in top. It really just depends on the wording of this part of the question. So this ends up being around 0.791. So that's 79.1%. So this top one, this is the proportion. Bottom one, that's the percentage. Either way you use it, we're okay, except if you use percentage, it needs a percent sign. So our 1 sample z-test for proportions. So we need to set up our hypotheses. So we can have our null hypothesis is going to be the same no matter what. It's going to be P, and it's always P. It's never P hat. No P hats in here ever. Is equal to P naught. So this value P naught, this is just a number value, and this is a number value that should never come from the sample. This should be a claim or a value of interest, but it doesn't come from the sample itself. We never put any sample information in the hypotheses. In general, you should be able to write the hypotheses before you see any sample data. So if you're using sample information at all in the hypotheses, that's a big no-no. We will jump on it every time. And then, like before, you can, if you have a not equal sign, you just want to know if there's a difference. That's a 2-sided test. So you would find your one-sided p-value, multiply by 2. You have a greater than or less than. So you can have a one-sided test as well. And it totally is going to depend on the wording of the question. If the question wants to know if there's a difference, or if the question is asking, hey, we think that this proportion is lower than claimed, that's what you're going to base this sign on. So here you have to find that you meet the conditions in order to move forward, although in general, if we don't meet them, we will make a note that they're not met, but we'll still continue. But absolutely, if you're not meeting them, it can be really problematic. So here, and note, the size condition in particular is different for a hypothesis test and a confidence interval. They are really similar, but they're a little bit different, so watch out. This number 1, this is always going to be true. We want to have a random sample. We want to have a random sample that we can say, yes, this represents the population. Because if we take a bad sample and we know it doesn't represent the population, this is super problematic and it's not very good. Then the size condition. So here so n times p naught is greater than or equal to 10. What that translates into is if the proportion is what's claimed in the null hypothesis, if that's true, did we take a big enough sample that we could have expected at least 10? And then on the flip side there, did we take a big enough sample size that we could have expected enough failures, like at least 10 failures? So we want to know if we could have expected at least 10 successes and at least 10 failures if the null is true and the proportion is what's claimed, given our sample size. And then if you can say that those two conditions are met, we would look at a z-test statistic. So you'd say, okay, well, I observed p hat from the sample minus what's claimed, and then in the denominator, the p's that go under the square root are p naughts. And that's because we're assuming the null is true. By default, we need to assume the null is true, so we need p naughts in the denominator. Really, really important. P naughts under the square root. So returning to our marijuana question, I looked up a poll on Pew Research, and it claims that 59% of Americans agree that marijuana should be legal at the federal level. Is there evidence that OSU student opinions are different than this claim? So, things to note, OSU students. So this is the group, the broader group that I want to make a statement about. This is hinting at my population. And then different than, that's going to definitely come into play here. Because we don't necessarily suspect that OSU students are higher or lower. We just want to know if they're different. So our first step is our question of interest. Is the proportion of OSU students that favor federal legalization of recreational marijuana different from 0.59? So is that proportion different? So this is a hypothesis test. It should be a yes or no question. We just want to know, hey, is the proportion of population, so all OSU students, that the variable of interest favor legalization, is it different from 0.59? And note that 0.59 comes from this other study that I read. It does not come from our sample. It has nothing to do with the sample itself. It has to do with an outside claim. So then my hypotheses, they should have p's in them. So my null, that population proportion p is equal to 0.59. We're just going to say, hey, we're going to assume the proportion is whatever's claimed. And we, for the alternative, just want to know, is it different? So we have a not equal sign. So this p-value, it's going to be two-sided because we don't have a strong opinion whether or not it would be higher or lower. We just want to know if it's different. And then we're going to assume a significance level of 0.05. It didn't say in there, so in general, if it has no statement as to what the significance level is, we can generally assume 0.05. Know also if they set a specific confidence level, the significance level that goes with that is probably the most practical. So like later, we're going to do a 95% confidence interval. That goes with a 0.05 significance level. That kind of idea. So checking our conditions, is the sample representative of the population? This one's iffy. I would argue, not really, right? This was definitely an example of a convenience sample. I sampled all of my students who are people that I have, easier access to. I didn't sample from all students. There were definitely, anybody who's not signed up in my class was not eligible to be part of this survey. So, it's not the best in practice. It's probably worth an asterisk at the end when we do our write-up. Like, hey, note, this probably doesn't represent the whole population. But we're gonna proceed. So then, n times p naught is that at least 10? So if I had 273 in my sample times what's claimed is 0.59, you see, I'm going to have to pull out a calculator for this one because my math is not that fast. Not my mental math anyway. So 273. So I get 161.07. So on average, if I were to repeatedly take samples of 273 and 59% of them had supported a legalization, I'd expect around 161. So yeah, that's at least 10 for sure. This is good. Then I want to know, hey, if I would expect around 161 successes, and I'm totally doing air quotes here, would I expect at least 10 failures? And hint, yes, because 161 plus something is 273. That something is definitely bigger than 10. So 273 times 1 minus P naught, so 0.41. So 273. So I get 111.93. Note, if I took these two numbers and added them, I would get 273. So this is at least 10 as well. So yes, if 59% of, if the null is true and 59% of everyone agrees with or approves, then if I took a sample of 273, I would expect at least 10 in each category. So yes, this will be okay. So then calculating my test statistic, things to note, so P naught is at 0.59. P hat, that is that 216 divided by 273, rounding, it's about 0.791. Then N, that's just how many were in the sample total, 273. So now I have everything you need to plug in. So about 0.79 minus, and note, when I threw this in my calculator, I didn't have rounding for this part. I had just 216 over 273. Not the biggest deal though. 0.59. So then the square root, so 0.59 times 1 minus that, that's 0.41. Divided by sample size, 273. It's going to be big, which isn't really too surprising. That's about 6.76. This is really big. In general, if you get a z statistic that's further away from 0 than 3, so like if it's lower than -3 or higher than +3, it means you're going to have a very small p-value. And the p-value is going to be really tiny. If you use the table, you can pretty much conclude that it's less than 0.0002. But, I mean, it is going to actually be even smaller than that. So, based on this, so the p-value, it's less than 0.0002. It's honestly, it's less than 1 in a million. It's really, really small. So looking at this spectrum here, our p-value is somewhere over here. So I would argue we have very strong evidence, very strong, convincing evidence that the true population proportion of Oregon State University students that approve legalizing marijuana federally is different than 59%, which isn't really super surprising when we observed in our sample 79% That definitely seems different to me personally than 59%, especially when we have a sample of over 200 people. So confidence interval. So if we know that p hat follows a normal distribution, we're going to use a z confidence interval. So we're going to start with our point estimate, so p hat plus or minus. We get to use a z star again, which is great. Anytime we use z methods, we get to use a z star. Z star confidence, z star. So anytime we have that, we get to use a z star critical value times a standard error there. So I like to put parentheses here. You don't have to. It reminds me to do the multiplication first. So our point estimate, so p hat plus or minus, so our z star critical value times square root of p hat 1 minus p hat over root n. Note here, this is p hat. Confidence intervals only want whatever you have in your sample. They do not care. They don't want to know anything about p naught. There should never be p naught involved with a confidence interval. So p naught never ever belongs in the confidence interval ever. We will flip out every time. So we do have conditions. We want to make sure that we have a representative sample. So we're looking at random sample. This is pretty much always going to be true no matter what methods we're using. We're going to want a random or representative sample. This condition is going to be slightly different. So slightly different than it was for the hypothesis test. Honestly, this one's easier in some senses. So n times p hat is at least 10. N times 1 minus p hat is at least 10. Translation, do I have at least 10 successes in the sample that I saw? And do I have at least 10 failures in the sample that I saw? So if I even throw back to the marijuana example, as long as I had at least 10 people vote each way, we're good to go. So looking here, we had 273. If I want to calculate a 95% confidence interval, my z star is going to be 1.96. You're welcome to memorize them. You don't have to. Absolutely, we usually give a table of the z star critical values. And then p hat, that's that 216 divided by 273. And that's going to be around 0.791. So looking here, I had 216 successes and I had 57 failures. I'm putting them in quotes. You don't have to. I'm just commenting. So both of those values are at least 10. So we're good on the sample size condition there. So here, if I want to, it'll be p hat plus or minus z star times square root p hat 1 minus p hat over root n. So I now have everything I need to plug in here. So note, I actually left as 216 over 273. It's okay if you round to the 0.791, but my answer I didn't round until the very end. Plus or minus, 1.96 times 0.79. always go at least 2 places past the decimal. Honestly, most of the time I'll go further out. When I actually plugged this into my calculator, I didn't round the 216 over 273, so if you get slightly different answers, that's most likely why. 273. Plug into a calculator. This is definitely not doing your head math, at least not for me. So without any rounding until the very end, I got 0.7430 all the way to 0.8394. So things to note, these are proportions, so we do not have units. And not only that, so if the value on the lower end goes below 0, you should cut it off at 0. You cannot have negative proportions, single proportions. If this value here at the top goes higher than 1, you should cut it off at 1, because a single proportion can't go higher than 1. So just keep that in mind. So yeah, our 95% confidence interval for the true proportion of all OSU students that approve of legalizing recreational marijuana at the federal level is between 74.3% and 83.94%, with a point estimate of the 79.1%. So choosing a sample size. So this is a throwback to, I want to calculate a sample size. So you have to pick a minimal margin of error. So you will have to decide, I want to have a confidence level, pick a specific confidence level, and I don't want my interval to be any wider than a set amount. So you pick a margin of error. And your margin of error, it's half of the entire length of your interval, because it's your point estimate plus or minus that margin of error. So your entire interval's 2 margin of error lengths long. So your margin of error, it's that critical value times your standard error. It's everything after, so you have your point estimate plus or minus your margin of error. It's everything that comes after the plus or minus sign. Anything afterwards, that's your margin of error. So then you have to get a method. So you need to have a big enough sample size to ensure that you have whatever level of confidence you set, and that your interval isn't any wider than the value you specified. And so we're going to end up using this notation here. So the Z star over your margin of error, so whatever you set, and it's in proportions, squared, times P star times 1 minus P star. So P star is going to be your best guess. So if you have no sample information, your best guess is going to be 0.5 or 0.50. That is just the most conservative guess you can guess. If you have sample information, use p hat. P hat's going to be your best guess if you have sample information. So throw back to our marijuana example. Suppose we want to have our estimate within 0.04 from the true population proportion. So ultimately, that's saying we want our width here. We want that width to be no more than 0.08 total. So that's going to be as wide as our interval can possibly get. And we want to have a 95% confidence interval. So how big of a sample size are we going to need? What's the minimal sample size we can get away with here? So 0.04, that's my margin of error. 95% confidence interval, I'm going to have the same Z star then, so 1.96. And P star, you can use 0.5 if you have no sample information. But since we do, it's going to be P hat. So that 0.791. And once again, this is a value where I think I plugged in the exact number. So you are going to plug in everything here on the right hand side. So this is going to be, so z star times margin of error squared times p star times 1 minus p star. That's equal to 1.96 for z star over 0.04 for my margin of error. Square that. So then times 0.791. I mean, I kept going. I did exact. But if you round a little bit, that's okay. 1 minus that. I end up getting something like 396.64. So putting it back together, I find that this is an important step. N is greater than or equal to 396.64. So if you think about it, you can't sample 396.64 OSU students, right? Somebody's going to get real miffed that you're like only talking to their arm. So you have to sample a whole number. Not only that is if you need it to be at least 396.64, 396 isn't going to be big enough. In this scenario, you must always round up. If you have a decimal, always round up. So N at least, so sample at least 397 OSU students. So in order to ensure that we have a 95% confidence interval that isn't any wider than 0.08 total, because our margin of error times 2 is 0.08, we need to take a sample of at least 397 OSU students. Which we didn't have, not in this case, but it's helpful to know, like how many more students would we have needed, kind of thing. In general, this is usually a really helpful calculation to do prior to actually collecting the sample. Ideally, you find out how many you need in your sample and then you go get that many. It's not as rewarding to go get your sample and then find how many more you would have needed. That's a lot more frustrating. I think that might be it for lesson 6. Nope, we have to put our conclusion together and then we'll get on to our 2 sample methods. So here, our p-value, it was less than 0.0002. That's really small. It's perfectly okay to put this. You could put in the exact value. It's really tiny. I want to say it's like 0 point and there's like at least 10 zeros before there's another number. It's really small. Do not round to 0 though. We will freak out every time you round a p-value down to 0, because a p-value of 0 means what you observed in the sample is literally impossible. But that's not true because we observed it. So we don't like that. Oh no. At 0.05, significance level. So if your p-value is really small and smaller than the significance level, we should reject that null hypothesis. We talked about the strength there. We said very strong. You might say convincing. Either way, the evidence, it was quite strong. That the proportion of all OSU students that approve of federal legalization of recreational marijuana is different than 0.59. This part is extra. It explains where 0.59 came from. But that's okay. You can totally include it. So the proportion of Americans that say marijuana should be legalized federally. We did a 95% confidence interval. So with 95% confidence, the true proportion of all OSU students that say recreational marijuana should be approved federally is estimated to be about between 0.7430 and always round these to at least 2 places past the decimal. 4 maybe not necessary. but I would recommend at least probably 2 minimum, but 3 is good. 3 is better. 8394 with a point estimate of, and this is going to be p hat from our sample, so 0.791. Of course, I didn't take note of what the next decimal was. Note here, though, I'm throwing in a disclaimer. So, disclaimer, since we did not take a random sample of all OSU students, these inferences may not really apply to all OSU students. Whether or not they apply to all stats students, that's a whole other. They probably don't, though. It really definitely, 100% this was a convenient sample. So I absolutely support throwing in a disclaimer saying, hey, this does not probably represent this population. But the conclusion should still be written in terms of the population. Like, it should still say the proportion of all OSU students and whatnot. It's okay to have a disclaimer that says, no, it doesn't. But the write-up should still be in terms of the population. And that's going to be it for Lesson 6. So now we're going to get on to comparing a proportion between two groups. So 2 populations, we want to compare the proportion. Are they different? Are they the same? Is one higher? And we'll see you there.